Hi, welcome to this lesson on radioactivity. And in this lesson, we're going to learn about a concept called half-life. Half-life is a really important quantity when considering radioactive isotopes and samples. Now, as we've learned before, radioactive decay is the random and spontaneous breakdown of heavy nuclei. The key word being random. And in this video, we're going to model how this random process ties in with the concept of half-life. Here we have 20 circles, and each circle represents a radioactive nucleus. Each nucleus, here we have 20 circles, and each circle represents a radioactive atom. These radioactive atoms will randomly break down. They will randomly decay. To model this random process, we are going to roll a die. We are going to roll a die for each radioactive atom. If a 6 is rolled, that atom will decay, it will break down and no longer be radioactive. This is similar to what happens in real life. Watch this process and follow closely. Let's roll the dice for this first atom. A 2 was rolled, so it doesn't decay. Let's keep going until an atom does decay and a 6 is rolled. So, this second atom decays because a 6 is rolled. Let's keep going. This third atom also decays as a 6 is rolled. Now let's keep going for all the atoms in this round. So, after the first round, round 1, we are left with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 radioactive atoms. Now let's move on to round 2. So for the first atom, let's roll the die. A 2 was rolled, so it doesn't decay. The second and third atoms have already decayed and are no longer radioactive. So these cannot decay again. So now we move on to the next radioactive atom, the fourth atom in this row. Hopefully you've started to understand how this works. Now I'm going to fast forward through this entire process. So our final results look like this in a table. We started off with 20 radioactive atoms, and we ended with 0. Every single radioactive atom decayed. And as they decayed, they broke down into smaller, lighter nuclei and released alpha, beta, and gamma radiation. The rate of this decay is known as the activity of a sample, and it's measured in becquerel. This measures how many nuclei decay every second, or how much alpha, beta, or gamma is emitted every second. Now, going back to the table, let's try plot this on a graph. Pause the video and have a go. So, let's plot it together now. On the y-axis, we have the number of radioactive atoms. More commonly, this is shown as the activity. And on the x-axis, we have a unit of time. But in this case, we have the round number. So we start off with 0. And at 0, we had 20 atoms. But very quickly, this began to drop, as at round 1, we only had 15 left. By the time we got to round 8, round 9, round 10, the vast majority of the atoms had already decayed, and we were left with just 2, 3, and 4 atoms in these rounds here. So the number of radioactive atoms reduces exponentially. And it took a very, very long time to get to 0. So our graph looks like this. This is a radioactive decay curve. It's also known as an exponential decay curve. Let's see what this might look like in your exams. First of all, it's a smooth curve. The y-axis is labeled as activity or count rate measured in becquerel, and the x-axis is a unit of time, whether that's days, years, or seconds. The curve always touches the y-axis, but never touches the x-axis. Now in our simulation, we used a die that rolled a 6 to simulate nuclear decay. However, in reality, each radioactive element and isotope has its own particular decay rate. This is shown by a distinct half-life for each radioactive sample. The half-life is the time it takes for the activity or the count rate of a radioactive source to decay by half. It's extremely important that you know this definition. Now let's relate this to our graph. So let's calculate the half-life of this iodine-131 sample. The half-life is the amount of time it takes for the count rate or the activity to decay by half. So initially, our count rate is 100. Half of 100 is 50. And the amount of time it took for this sample to decay by 50% is 8 days. So the half-life of this sample is 8 days. It's really important to note that as this sample decays by half again, from 50 to 25, this takes a further 8 days. And once again, as it decays from 25 to 12.5, decaying or reducing by half again, this takes a further 8 days again. Now let's try another one. Here we have a sample of technetium-99. Try and find the half-life of this sample. Pause the video and have a go. So, this sample has an initial activity of 1500 becquerel. Half of 1500 is 750. Now, using the graph, let's find the amount of time it took for this sample to decay by half, from 1500 becquerel to 750 becquerel. As we can see, it took 200,000 years. So the half-life of this sample is 200,000 years. Hopefully you got that right. This is how we identify the half-life of a sample graphically. But in some questions, we also need to identify the half-life of a sample numerically. Let's have a go at that now. These calculations often look difficult and often trick many students, but there is one easy way of doing it. You simply need to count how many times the source halves. Let's see how this works. In this question, the activity of a radioactive isotope is 640 counts per minute. 2 hours later, it has fallen to 80 counts per minute. Find the half-life of this sample. Initially, this isotope had an activity of 640 counts per minute. Half of 640 is 320. Half of 320 is 160. And half of 160 is 80. Remember, half-life is the amount of time it takes for the activity of a sample to half. In this case, this sample has undergone 3 half-lives. And this took a total time of 2 hours. So if the sample took 120 minutes for 3 half-lives, we can find that 1 half-life is equal to 40 minutes. By dividing both sides by 3. So our answer is 40 minutes. Let's try another. In this case, pause the video and have a go. In this question, the number of undecayed nuclei of a radioactive isotope drops from 32 to 8. If 1 half-life is 7 seconds, how long would this whole decay process take? Initially, we have 32 nuclei. Each half-life is 7 seconds. So to go from 32 to 16 takes 7 seconds. And to go from 16 to 8 takes a further 7 seconds. Here we can see the process undergoes 2 half-lives. If 1 half-life is 7 seconds, this whole process takes 14 seconds. Hopefully you got that right. I hope you found this video useful. If you have any questions, please do ask.